Good day. Welcome to our presentation on designing multi-component distillation column in partial fulfillment in the course of CHE 368 separation process proposed by Aliganga, Amparo, and yours truly, Anoba. So before going further for the calculations, let us first know what is distillation. So distillation is key in chemical engineering for separating liquids mixture components by boiling points. It's widely used in industries like petroleum refining and pharmaceuticals. So let us know what is the intent or the objective of designing a distillation column. So it is to find the best design parameters such as the number of stages, column diameter, height, and plate thickness for the distillation column, as well as to identify the potential challenges in designing a multi-component distillation column. So this presentation highlights designing a multi-component distillation column for separating C2 to C7 hydrocarbons. Thus, this aims to create a detailed CAD model of the column including all necessary equipment for a thorough visualization of the design. To start, we have table 1, the composition of components. So the given compositions of MCD is a mixture of hydrocarbons ranging from C2 to C7 is used as a multiple component feed, entering the fractionations as saturated liquid. The composition of feed and distillate are specified. The light key component is represented with cis-2-butene, whereas the heavy component is represented by the I-pentane. As you can see over here, we have eight components that is present. So ethane, propane, isobutane, cis-butene, I-pentane, isoprene, cyclohexane, and toluene. So for this one, the givens are already given are the feed molar fraction and the distillate molar fraction. So in order to obtain the each flow rates, which is F, D, and B, uh, the group used a basis of a feed flow rate of 100 kilomoles per hour. Then taking the light key component, which is the cis-butane, uh, we, we assume that we assumed a bottom mole fraction of 0.002. Then using the material balance equation for the light key component, we obtain the distillate flow rate. So continuing, we use the overall material balance equation to obtain the bottom flow rate, which is 55.2903 kilomole per hour. So once we get the flow rates, we can proceed in getting the bottom composition of each given components by using as well the material balance, but with the specific that has the specific components. Okay, so this part shows the equations used to obtain the components from table 1. So we use the overall material balance and the component material balances. So for this one, we have the F is equals to D plus W, wherein F is the feed flow rate, D is for the distillate flow rate, and W for the bottom flow rate. And then if you need to find the composition or the mole fraction of the composition, is that you use the FXF, or XF is represented with the feed mole fraction, is equals to D, then the mole fraction of distillate plus the bottom times the bottom distillate. So over here, there are two types of calculations that is represented, distillate and for the bottom. So it's just a simple mathematical method.
Vapor-liquid equilibrium is calculated using the Antoine equation. Log times vapor pressure is equals to A minus B over temperature plus C, where vapor pressure is in torr and ABC are the Antoine constants, which can be seen from Table 2 for the system C2 to C7, and T is the absolute temperature in Celsius, which is given 120 degrees Celsius. Table 3 presents the calculated distribution coefficients and relative volatilities for components C2 to C7. In this table, cis-butane highlighted in blue is identified as the light key component. It has a distribution coefficient of 1.551900682 and a relative volatility of 1.882425496. Meanwhile, isopentane, highlighted in red, is designated as the heavy key component with a distribution coefficient of 0.8244154605 and a relative volatility of 1. The values indicate that cisbutane is more volatile compared to isopentane as it has higher relative volatility, making it the light key component in this mixture. The distribution coefficients and relative volatilities listed in Table 3 can be calculated using specific equations. The relative volatility of component I is determined by dividing its vapor pressure by the vapor pressure of the heavy key component. This equation helps in understanding the ease with which a component can be separated from others during distillation. For the distribution coefficient of component I is calculated by dividing its vapor pressure by the given operating pressure. In this case, the operating pressure is specified as 13 bar, equivalent to 9,750.801910 torr. These calculations provide essential insights into the separation process and help identify the ease of separation between the components in the mixture.